If you look at the device you're listening to this on right now, whether it's a smartphone in your pocket or maybe a laptop on your desk, there's this inherent comfort in how we think it operates.
Oh, absolutely. We love the idea of predictability.
Right. We usually imagine computer science and logic as this ultimate realm of like absolute, unshakable precision. And it feels like engineering a skyscraper, you
Yeah,
know?
you have a massive blueprint, you lay the steel girders perfectly.
Exactly. And the rigid rules of physics dictate exactly how it stands. It's binary, it's deterministic, it's just clean. We like knowing that our computer processors are following a strict set of instructions, going from step A to step B to step C, without any, without any creative liberties at all.
It is a world built entirely on absolutes, right? A statement is universally true or is demonstrably false.
Yeah.
A microscopic circuit deep inside your phone's processor is open or it is closed. There's no middle ground there, and there's really no room for ambiguity. That predictability is essentially the foundation of the modern technological world.
But what happens when that pristine, rigid blueprint basically catches fire? Because today, we're taking you into a space where that illusion of absolute certainty completely breaks down.
It really does. It shatters.
We're exploring what happens when systems become so incredibly complex that the clean math we've relied on for decades it simply stops working. We are embarking on a deep dive that looks at an epistemic collision. It's a total clash of worldviews.
And researchers, they aren't just trying to build faster calculators anymore. They've hit a physical and mathematical wall,
Right. And to get past it, they're turning to the chaotic, stochastic, completely unpredictable processes of biological evolution.
which is, frankly, a profound paradigm shift.
Hmm.
We're applying what you could call a paraconsistent lens to everything from software to physical metal.
A paraconsistent lens.
Yeah, we're looking at the contradiction between rigid mathematical truth and the messy trial and error probability of biology.
Man, I love that.
And out of that contradiction, we're seeing unprecedented leaps. This is really the journey from contradiction to an entirely new opportunity, to a latent leap in capabilities, and finally to genuine discovery.
And the destination we are heading toward today is going to sound like pure science fiction, honestly. We aren't just talking about code that learns how to play chess or, recognize a face.
Not at all.
We're going to explore physical metal and silicon circuits that can literally heal themselves after taking physical damage, much like living biological tissue.
It's wild to even think about.
It is. We're going to talk about artificial intelligence that writes its own logic and foundational systems that actively reject the concept of absolute universal truth. It is a wild ride.
Yeah.
But to understand the biological leap, we first have to understand the wall.
The classical wall that computer science crashed into.
Exactly. And that starts with something called the Boolean satisfiability problem, or SAT.
Right. And the SAT problem is truly the bedrock of automated planning, of hardware design, and of artificial intelligence. In the realm of computer science, SAT is what we call the paradigmatic NP-complete problem.
Okay, wait, I'm going to stop you right there. Because if you're someone like prepping for a meeting or just trying to expand your knowledge base on your commute, throwing around terms like NP complete is a really quick way to lose the thread.
That's a fair point, yeah.
Let's break that down. What does NP complete actually mean for you listening right now?
Without getting into the heavy mathematical notation, think of NP-complete problems as a specific family of puzzles that share two unique traits. First, if I hand you a proposed solution to the puzzle, you can verify whether it is correct very quickly.
Okay, so checking the answer is fast.
Exactly. But second, actually finding that answer from scratch is incredibly slow and complex. And as the puzzle gets bigger, the time it takes to find the solution grows exponentially. The complete part of NP-complete means that this problem is the master key. If you can find a fast, efficient way to solve the SAT problem, you automatically have a fast way to solve every other complex problem in that family.
Wow, really? Every single one?
Every single one. From routing delivery trucks across the globe to folding complex proteins. They're all mathematically equivalent under the hood.
That puts a massive bounty on the SAT problem then. So what actually is it? If I'm trying to solve SAT, what am I literally looking at?
You're looking at a massive Boolean formula. Imagine a very long string of logical variables. Let's call them variable X, variable Y, variable Z.
Okay, tracking.
Each of these variables can only hold one of two states, true or false. And they are all connected by simple logical operators like AND, OR, and NOT.
Right, the basics.
The SAT problem asks one fundamental question. Is there any possible combination of true and false assignments for all of these variables that makes the entire massive formula evaluate to true?
I'm trying to picture this. It sounds a bit like trying to arrange a massive wedding seating chart where everyone has conflicting demands.
That's a great way to put it.
Like Uncle Bob will only attend IF, Aunt Susan is there, A&D, Cousin Larry is not there, but Aunt Susan will only come IF, the open bar is true, or the DJ is false.
That is a brilliant way to visualize it. Each of those demands is what we call a clause. So the formula is made up of thousands of these individual clauses.
Okay.
To solve the problem, to have a successful wedding, every single clause must be satisfied. If even one clause evaluates to false, like if Uncle Bob is seated next to Cousin Larry, the entire formula collapses. The result is false.
Got it. Now, on a small scale, that sounds tedious but totally manageable. If I only have 3 guests, I can just write out every possible scenario on a napkin, right?
That's true, yeah.
True, true, true. True, 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 false. I just systematically try every combination until I find one that works or I prove that it's impossible.
And that systematic approach is essentially a deterministic solver. It is guaranteed to find the truth eventually. And the classical deterministic solvers that the software industry has relied on for years are just incredibly sophisticated, hyper-optimized versions of your napkin math.
Oh, really?
Yeah. For example, there are algorithms like DPLL and its modern successor called CDCL, which stands for Conflict-Driven Clause Learning.
Okay, so how does a conflict-driven solver improve on just blindly guessing every combination?
It learns from the dead ends. Let's use a Sudoku puzzle as an analogy. Imagine you were solving a massive Sudoku and you place a 5 in the top left corner. You play for 20 minutes, filling in numbers until you suddenly realize you have trapped yourself.
Oh, I hate that.
Right. You need to place a 9, but there is no legal spot for it. Now, a basic solver would just erase the whole board, change that initial 5 to a 6, and start blindly guessing again. It has no memory.
So it's just pure brute force.
Exactly. But CDCL is different. When it hits that trap, the conflict, it pauses. It mathematically analyzes the exact sequence of choices that led to the trap.
Wait, it analyzes its own failure?
Yes. And it dynamically writes a brand new rule, a new clause, and adds it to the master formula. It essentially says, I have mathematically proven that if the middle square is a 4, the top corner can never be a 5. Never try any combination that includes both.
Oh, wow.
By learning from the conflict, it permanently prunes vast, sprawling branches of the search space. It never repeats a structural mistake.
That sounds incredibly smart. You are dynamically shrinking the universe of possibilities every time you fail. But I assume this brings us to the wall.
It does.
Because if I am synthesizing a modern microprocessor or verifying the security of a cryptographic algorithm, I don't just have Uncle Bob and Aunt Susan. I have a formula with millions of variables.
Millions of variables and tens of millions of clauses. And this is exactly where the classical deterministic approach completely breaks down. This is the scalability wall.
Because there's just too many combinations.
Right, because the number of possible combinations grows exponentially. Every time you add just one single variable to the problem, you double the total number of combinations you might have to check.
Double it, wow.
2 to the power of a million is a number so staggeringly large that the human brain cannot even comprehend it.
But wait, let me push back on this a little bit. Technology scales. We see it every day. If deterministic math is hitting a wall because the problem is too big, why isn't the solution just build a bigger bulldozer?
So common thought, yeah.
Why can't we use quantum computing or massive cloud-based parallel processing and just blast our way through the combinations?
It is a common intuition, but it fundamentally misunderstands the brutal reality of exponential growth. Let's say you spend $1 billion and invent a supercomputer that is exactly 1 million times faster than the best machine we have today.
Okay, 1,000,000 times faster.
1 million times faster. You boot it up to solve a SAT problem because the search space doubles with every new variable. That million-fold increase in speed only buys you roughly 20 additional variables before you hit the exact same computational wall.
Wait, really? Just 20?
Just 20. You solve a puzzle with 1,020 variables instead of 1,000, and the universe ends before the machine can finish the next step. You cannot outcompute exponential complexity with brute force hardware.
That is mind-blowing.
The blueprint approach is dead. You need a latent leap in how you actually search for the answer.
So we have to abandon the systematic deterministic napkin math entirely. We can't guarantee we will check every path. And that leap, according to the research we're looking at, is biology.
Biology, specifically evolutionary algorithms or EAs. We introduce stochastic biological metaphors, trial, error, and survival of the fittest.
I need to pause and really lean into the epistemic dissonance here because this is the exact moment my brain started to glitch when I was reading the source material.
It's a tough pill to swallow for computer scientists.
Right. We are talking about solving the absolute strictest, most rigid, unforgiving binary logic problems imaginable. Boolean satisfiability, the literal ones and zeros of computer science. If a single clause is wrong, the motherboard doesn't boot.
Exactly.
And to solve this pristine mathematical glass house, researchers are essentially scooping up a handful of genetic spaghetti, throwing it at the wall, and letting Darwin figure it out.
It is a profound contradiction. You are taking the chaotic, random mutations of biological evolution and using them to hunt down the perfect singular order of mathematical logic.
So walk me through this. How do you literally evolve a math solution? I understand a wolf evolving thicker fur to survive the winter, but how does an equation evolve?
Well, you start by generating a population of completely random guesses. Imagine the system spits out 10,000 different random assignments of true and false for your millions of variables.
Okay, just total gibberish guesses.
Total gibberish. These 10,000 guesses are your initial individuals in the population. The vast majority of them are going to be terrible, but you need a way to measure them. So you introduce an environment, which in algorithmic terms is a fitness function.
The survival pressure. And in the context of SAT, the sources refer to this as the MaxSat fitness function. What is that actually measuring?
MaxSat is beautifully simple. It just tallies up the score. It looks at a random guess, runs it through the millions of clauses, and counts how many individual clauses it accidentally satisfies.
Oh, I see.
So if individual A satisfies 100,000 clauses and individual B satisfies 105,000 clauses, individual B is considered more fit for the environment.
It survived the winter better.
Precisely. So the algorithm applies the mechanism of selection. It kills off the weak individuals, the ones with low scores, and allows the high scores to survive and reproduce.
And how do math guesses reproduce?
Through a mechanism called crossover. The algorithm takes the genes, the specific string of true and false assignments from two highly fit parents, and splices them together to create an offspring.
Like actual DNA.
Exactly. Maybe the first half of the variables comes from parent A, and the second half comes from parent B. You're hoping that by recombining the traits of successful individuals, the offspring will inherit the best parts of both and achieve an even higher MaxSat score.
And then there's mutation, right?
Yes. Every so often, the algorithm will just randomly reach into an offspring's genetic code and flip a single bit. It changes a true to a false, purely by chance.
Just to inject some chaos. But why do you want chaos if you are trying to optimize?
Because without genetic diversity, the population becomes inbred and gets stuck. Mutation ensures the evolving population is always exploring new, weird areas of the logical landscape that they might never reach just by recombining their existing traits.
Okay, conceptually, that paints a great picture. We are breeding logical solutions. But the research explicitly points out that if you just take a standard, off-the-shelf classical genetic algorithm and unleash it on a massive SAT problem, it fails spectacularly.
It does. It crashes and burns.
It doesn't find the perfect solution. Why? If evolution is the ultimate problem solver in nature, why does standard Darwinism choke on my computer circuit?
Because the mathematical landscape of a SAT problem is incredibly hostile and deceptive to evolution. The technical term the researchers use is misleading low-order schema information.
Which means absolutely nothing to me. Let's translate that.
Let's use a physical analogy. Imagine you are trying to hike to the absolute highest peak in a massive, sprawling mountain range. The rule is you have to find the one true summit. But you are completely blindfolded.
Okay, blindfolded in the mountains sounds dangerous.
Very. All you can do is feel the ground immediately around your boots. If the ground slopes up, you take a step in that direction. That is essentially what a basic genetic algorithm does. It follows the upward gradient of fitness.
Makes sense. Keep walking uphill, you eventually hit the top of the mountain.
In a normal landscape, yes. But the misleading schema of a SAT problem means the landscape isn't shaped like a normal mountain. It is mostly a vast, flat plain dotted with millions of tiny false hills.
Oh, I see where this is going.
So your population of blindfolded hikers starts walking. They feel a slight incline, they follow it, and very quickly they reach the top of a small mound. They feel around with their boots. Every single step they take in any direction goes downhill. Their MaxSat score drops.
So they stop.
They stop. They think, we made it. This is the highest point in the world. The algorithm stalls out, entirely convinced it has found the best possible answer.
Because it can't see the massive Mount Everest sitting 5 miles away. To get to Everest, they would have to walk down off their little hill, cross a deep valley of terrible fitness scores, and start climbing again.
Exactly.
But the evolutionary rule is survival of the fittest. Walking down into the valley kills them. So the genetic spaghetti just sticks to the ceiling of that tiny false peak and stays there forever.
That is the perfect visualization of a local optimum. To fix this, you cannot just change the hikers. You have to adapt the environment itself. You have to change the shape of the world.
Change the world itself.
And this leads us to the specific adaptations developed for SAT, the most fascinating of which is SOEA, stepwise adaptation of weights.
I spent a lot of time reading this section on Surveya, and I have to say, it felt almost like psychological warfare against the algorithm. It is manipulating the very fabric of the reality the individuals are evolving in.
It is a profound shift in environmental pressure.
Right.
Walk us through how you understood it.
Okay, so imagine the MaxSat fitness function again. Initially, every single clause in the massive formula is worth exactly 1 point. All clauses are created equal, the population evolves, and as you said, they quickly get stuck on a false peak. They figure out how to satisfy 90% of the clauses, but that last 10% is just too hard, and they stall. In a normal system, game over.
But SOEA doesn't accept the stall.
No, it pauses the simulation. Every 250 generations or so, the system freezes time. It looks at the absolute fittest individual in the current population, and it ignores everything that individual got right. It only looks at the specific stubborn clauses that the individual is still getting wrong. And so WEA reaches in and assigns a penalty weight to those specific clauses. It makes them heavier. It says, okay, solving these easy clauses is no longer worth 1 point, but solving this hard clause over here, that's now worth 10 points.
It creates a massive artificial incentive.
It literally alters the gravitational pull of the fitness landscape. If the hikers are stuck on that false peak, refusing to walk down into the valley, so WEA essentially uses magic to inflate the valley floor until it pushes the hikers off their hill.
I love that visual.
It tells the evolving population, I don't care how many easy problems you solve. If you don't evolve to solve these specific difficult bottlenecks, your fitness score is going to plummet and you are going to die.
And the population is forced to adapt. It forces the mutations to cluster around the most difficult aspects of the logic puzzle. The researchers found that this stepwise adaptation allows the evolutionary algorithm to escape those local optimizels and relentlessly hunt down the global truth.
Wow.
It is the perfect synthesis of the paraconsistent lens. You are utilizing an ever-changing adaptive biological environment to forcefully guide random mutations toward a singular deterministic mathematical truth. Order born from manipulated chaos.
That is a brilliant transition, because if we can use this kind of manipulated biological evolution to solve abstract software logic, the next question the researchers asked was, what happens when we unleash these algorithms on physical reality?
That's where things get really crazy.
We're moving from the abstract space of variables and equations into the tangible realm of voltage, metal, and silicon wires.
We are entering the domain of evolvable hardware, or EHW.
Yeah.
And this is where the implications move from clever mathematics to something that sounds like the T-1000 from Terminator.
Evolvable hardware. The foundational concept here is that electronic systems, physical circuits, can autonomously adapt, optimize, and reconfigure themselves in real time to respond to changing environments or incredibly hardware failures. But my immediate hurdle with this is the physics of it. How do you evolve a physical circuit? I can't just take my laptop's motherboard, melt it down, stir it around with an algorithm, and hope it solidifies into a faster graphics card. Hardware is hard, it's etched.
You are totally correct.
Yeah.
That you cannot evolve a traditional ASIC, an application-specific integrated circuit like the processor currently running your laptop. Those are built like concrete houses. The walls are where they are.
Right.
The logic gates, the physical microscopic switches that perform the ANDs and ORs are permanently etched into the silicon wafer. If you want to change the floor plan of that house, you have to demolish it, go back to the fabrication plant, and print a new chip.
So what is the canvas for evolvable hardware then?
It is a piece of technology called an FPGA, a field programmable gate array.
So instead of a concrete house?
Think of an FPGA as a massive, empty warehouse filled with millions of generic, unassigned logic blocks and an incredibly complex grid of programmable wiring connecting them all. The hardware doesn't have a fixed identity.
Instead, it relies on a configuration file, a stream of data loaded into its memory. That file tells the FPGA, turn block A into an AND gate, turn block B into a multiplier, and route the physical electrical current from A to B.
So the hardware is malleable. You can load a new configuration file in a matter of milliseconds, and the actual physical pathways of the electrons will change. Your chip can physically wire itself to be a video decoder at 1 p.m. and rewire itself to act as an audio synthesizer at 1.01 p.m.
Exactly. The FPGA provides the reprogrammable physical substrate necessary for an evolutionary algorithm to do its work.
Okay, so it can test things physically.
Yes. The algorithm can generate a random configuration file, load it onto the FPGA, run electrical current through it to see how well it performs a task, and then mutate the file and try again, all in fractions of a second.
It is the ultimate petri dish for silicon evolution, and the methodology that really cracked this open was developed around 1999 and 2000 by a researcher named Julian Miller. It's called Cartesian Genetic Programming, or CGP. CGP was a massive leap forward because it abandoned the old ways of representing code. Early genetic programming tried to evolve code structured like a massive branching family tree. It was clunky and didn't map well to physical hardware.
A family tree of code.
Yeah, it was a mess. Julian Miller realized that physical circuits are better represented as a grid, Cartesian, like a Cartesian coordinate system.
The sources mention that CGP uses directed acyclic graphs, or DAGs, which again is heavy jargon.
A directed acyclic graph is actually a very simple visual concept. Imagine water flowing down a mountainside. The water moves in a specific direction downward. That's the directed part.
Okay.
And it never flows back up to create a whirlpool or an infinite loop. That's the cyclic part. It only flows forward. In CGP, the logic gates are arranged in a 2D grid, and the electrical signal flows strictly forward from the inputs on the left to the outputs on the right.
The analogy I kept coming back to while reading about CGP's structure is a modular synthesizer, or maybe a futuristic, highly advanced Lego board.
Oh, the Lego board is a great way to look at it.
Imagine you have this grid of blank Lego blocks. Every block can be programmed to perform a specific function. Maybe this one adds numbers, maybe this one compares them. And you have an unlimited pile of patch cables to connect them. CGP uses an address-based genotype.
Right, the string of integers.
Yeah. The genetic code isn't a string of true and false. It's a long string of integers that acts as the blueprint. It essentially tells the system, take a patch cable, plug the output of block 3 into the input of block 12, and then program block 12 to act as an OR gate.
That analogy holds up perfectly. The evolutionary algorithm is mutating that specific string of integers. It randomly swaps a virtual patch cable from block 12 to block 15, or it mutates the instruction for block 12 so it becomes an AND gate instead.
And then it measures what happens.
Exactly. Then it measures the output. Did that random swap make the circuit process an image filter slightly faster? If yes, that integer string survives and breeds.
But reading further into the mechanics of CGP, I hit a massive aha moment. There is a secret sauce to Cartesian genetic programming that makes it so incredibly powerful for evolving complex hardware. And it's something that, again, feels like a direct ripoff from biology. It is the concept of neutrality.
Neutrality.
Yeah.
Or neutral drift. If you want to understand how evolvable hardware actually succeeds, this is arguably the single most important mechanism.
I have to admit, when I first read the definition, it sounded like a design flaw. It sounds like the algorithm is just wasting space and doing nothing.
In classical engineering, it would absolutely be viewed as a flaw.
Yeah.
In CGP, the genotype, the full list of patch cable instructions, is almost always significantly larger than the actual functional circuit that gets built. You might have a grid of 100 blocks, but only 20 of them are actually wired up to the final output pin.
So there are 80 blocks sitting on the Lego board that might have functions assigned to them, and they might even be connected to each other, but their outputs are just dangling. They aren't plugged into the final speaker. They are disconnected from the end user.
Yes. These are explicit, redundant, inactive genes. They do not affect the phenotype. In other words, the final behavior of the circuit is entirely unaffected by what those 80 blocks are doing, because their signal never reaches the finish line.
And a classical human engineer would look at that and scream, inefficiency. Delete those 80 blocks, clean up the code, optimize it.
Right. A human engineer seeks a tight, minimalist blueprint. But an evolutionary system thrives on the messy surplus. As the evolutionary algorithm runs generation after generation, mutations aren't just happening to the 20 active blocks.
They're mutating the inactive ones too.
Exactly. Mutations are also randomly hitting those 80 disconnected blocks. The patch cables between those inactive blocks are swapping. Their functions are changing. They are exploring millions of new configurations in the dark, completely invisibly.
And because they are disconnected from the output, these mutations don't change the fitness score of the circuit. The score doesn't get better. But crucially, it doesn't get worse either. The mutations are neutral, the circuit just drifts sideways.
And this is how you cross the valleys. Go back to our blindfolded hikers stuck on the false peak. They couldn't take a step down because it lowered their fitness score. But imagine if they had a drone they could send out over the valley.
Oh, that's clever.
The drone flying around doesn't change the hiker's altitude. It's neutral. The drone can explore the entire valley, fly all the way over to Mount Everest, and drop a rope bridge right back to the hikers.
So in the circuit, those inactive blocks are the drone. They can spend thousands of generations silently building a massive, highly complex, incredibly optimal subcircuit in the background.
Yes, silently exploring.
They can suffer terrible mutations and brilliant mutations, and the main circuit's survival is never threatened because the subcircuit is unplugged, and then generation 10,000 hits.
A single random lucky mutation takes the output cable of that massive invisible subcircuit and plugs it into the main output line.
Boom. The bridge is crossed. The phenotype radically transforms in a single generation, the fitness score skyrockets, and the population leaks entirely over the valley of bad scores. It is functional redundancy. It's having multiple different tools being built in the shed just waiting for the day the environment demands them.
The research data backs this up overwhelmingly. Studies on evolving things like 3-bit Boolean multipliers, complex mathematical circuits, show that if you restrict the genotype size and remove that redundant space, the evolution almost always stalls out. It gets trapped.
It needs the junk space.
Yes. But when you enable neutral mutations, the success rate drastically improves. The system needs room to dream, essentially.
It really reminds me of how we used to view junk DNA in the human genome. For a long time, scientists thought massive portions of our DNA did absolutely nothing. It was just evolutionary baggage.
Exactly. We thought it was useless.
But now we understand that a lot of that non-coding DNA acts as a regulatory sandbox. It's a space where evolution can tinker and assemble new genetic combinations without fatally mutating the core functions of the organism.
It is the exact same principle, mathematically formalized in silicon. And the real-world applications of this neutral drift are straight out of a science fiction novel. This is where we look at embryonic systems.
Yes, the self-healing hardware. Let's paint a picture for you listening, because this is where the theory becomes incredibly tangible.
Imagine a high-stakes aerospace application. A deep space probe is halfway to Jupiter. It is constantly being bombarded by cosmic radiation. Suddenly, a high-energy particle strikes the main FPGA chip, and a physical cluster of microscopic transistors is permanently destroyed, vaporized.
If that probe is running on a classical deterministic architecture, that chip is dead. The blueprint requires those specific transistors to be there. The circuit is broken, the probe goes dark, and the billion-dollar mission is over.
But if that probe is running an evolvable hardware architecture,
the system senses the fault. It realizes the output is suddenly generating errors.
the evolutionary algorithm immediately kicks in. It takes the surviving, intact logic blocks on the FPGA, and it starts mutating the configuration file. It leverages all of that neutral drift, utilizing the inactive blocks, rapidly rewiring the virtual patch cables around the physical crater on the chip.
While it's flying through space.
While it's flying.
Yeah.
It tests thousands of new configurations a second, evaluating their fitness.
Until it discovers a brand new layout that restores 100% functionality without using the destroyed transistors. The circuit literally heals itself by growing around the wound, like a tree growing around a fence post.
Or imagine a semi-autonomous robot exploring a hostile environment, like a Mars rover. It suffers mechanical damage and breaks one of its motorized legs. A traditional control system would just keep trying to walk normally and end up spinning in circles.
Right.
An EHW system senses the physical change in its environment and evolves an entirely new gait on the fly. It learns to limp efficiently. It invents a completely new reality based on the current constraints.
It doesn't rely on a pre-programmed backup plan from an engineer on Earth. It constructs the solution locally, which is a profound shift in how we view logic systems. It suggests that the truth of a circuit or the validity of a system isn't some fixed, eternal blueprint stored in a textbook.
It's an ongoing construction.
Exactly. It is something that has to be continuously built, tested, and proven in response to the friction of reality.
Which brings us to the most fascinating pivot in this entire discussion. Because what you just described, the idea that truth is not a pre-existing absolute, but an ongoing algorithmic construction, is the exact paradigm shift that tore through the philosophy of mathematics over a century ago.
We're moving from the physical tangibility of FPGAs to the deep metaphysics of logic itself. Let's leave the hardware behind for a moment and look at pure philosophy. I want to introduce you to a Dutch mathematician named L.E.J. Brouwer and his brilliant student, Arend Heyting.
They really shook things up.
They did. Between roughly 1907 and 1928, they developed a philosophical framework called intuitionistic logic. And they essentially declared intellectual war on classical mathematics.
They did. And to understand why, you have to understand the classical view they were attacking. Most of us, implicitly, are Platonists when it comes to math. We believe that numbers and equations are objective, mind-independent properties of the universe.
So if they're just out there waiting to be found.
Right. We think the number 7 exists out there in the ether floating around, and humans merely discovered it.
But Brouwer looked at that and said no. Brouwer viewed mathematics strictly as an act of human mental construction. Math doesn't exist out in the void. It only exists inside the mind that is actively building it, step by step.
It is a radically constructivist view.
Here's where it gets really interesting, because intuitionism doesn't just offer a different flavor or interpretation of math. It actively, aggressively rejects the classical rules of logic that we take for granted every single day, the very rules that our standard computer processors are built on.
The most famous, and perhaps the most jarring rejection, is their refusal to accept the law of excluded middle, or LEM.
The idea that it's either A or it's not A.
Right. In classical Boolean logic, a statement is either true or it is false. A light switch is on or it is off. There's no middle ground. And classically, mathematicians use this assumption as a powerful tool to prove things. You can say, well, I don't know exactly what the answer is, but it must be A because I can show that the alternative, not A, is impossible.
It's the ultimate process of elimination. But intuitionists look at that and say, hold on, that process of elimination only works if you are dealing with a finite, closed system where you can look at every single option, like a deck of cards.
Right, the deck is finite.
Exactly. The top card is either the ace of spades or it's not. I can prove that by looking through the remaining 51 cards.
But mathematics deals heavily in infinities.
Yeah.
Brouwer argued that asserting a disjunction saying AOR not I is not a free pass. To make that claim, you must possess a definitive algorithmic proof of one or the other. You cannot blindly assert that one must be true if you're dealing with infinite collections where a systematic check is impossible.
The sources provided a perfect mathematical example for this, the twin primes conjecture. Let's walk through this so you listening can feel the difference between the two philosophies.
Twin primes are simply prime numbers that are exactly 2 integers apart, so 3 and 5, or 11 and 13, or 41 and 43. The conjecture asks a very simple question. Are there infinitely many pairs of twin primes as you count up toward infinity?
And despite centuries of trying, humanity still does not know the answer.
We do not. Now, if you were a classical logician, you would stand at a chalkboard and declare either there are infinite twin primes or there are not infinite twin primes.
Yeah.
The law of excluded middle holds. It is an objective fact of the universe locked away in the ether, even if human beings haven't figured it out yet.
But if you are an intuitionistic logician,
You look at the chalkboard and say, that statement is mathematically invalid. Under intuitionistic logic, you cannot assert A or R not A for the twin primes conjecture. Why? Because we currently possess no general algorithm to decide it.
we haven't built the bridge.
Exactly. We have not built a constructive proof that they are infinite, that's A. And we have not built a constructive proof that they are finite, that's not A. Therefore, the overarching statement A or R not A simply does not exist. Truth must be constructed. If you haven't built the algorithmic bridge to the answer, the truth has no reality.
That is a heavy concept. It feels almost like quantum superposition applied to mathematics. The state isn't determined until you force the measurement through an algorithm. But intuitionism goes even further down the rabbit hole. They also completely reject the concept of double negation elimination, or DNE.
In classical logic, double negation is simple. Not A is mathematically identical to A. Two negatives cancel out and make a positive. If I prove that it is false that I am not hungry, the only logical conclusion is that I am hungry.
But Brouwer and Heyting say, absolutely not. In their framework, proving that a proposition is not false only proves one thing, that assuming it is false leads to a logical contradiction. That's it.
It doesn't give you the answer.
Right. It provides no localized, positive, algorithmic blueprint for the actual truth of A. Demonstrating that the absence of an object is impossible does not magically conjure the object itself into physical existence.
The analogy you mentioned in your notes for this was quite striking. You called intuitionism the ultimate picks or it didn't happen logic.
Yes. I was trying to ground this in everyday reasoning. Think about a high-stakes criminal trial. In classical logic, a prosecutor could theoretically convict a suspect by proving that it was absolutely physically impossible for any other human being on Earth to have committed the crime.
By process of elimination.
Right. They use the process of elimination. They prove that the idea of the suspect being innocent leads to a paradox. Therefore, by default, the suspect is guilty. Not guilty equals guilty.
It is a conviction by elimination.
But under intuitionistic logic, that argument is thrown out of court. You cannot just prove the impossibility of their innocence. To get a conviction, you must physically produce the algorithmic murder weapon. You need a positive construction of the event. You have to build the bridge from the premise to the conclusion, step by step, showing exactly how they did it.
I am tracking with you. And to formalize this incredibly strict standard of truth, modern logicians use a visual and mathematical framework called Kripke semantics.
Yes, Kripke models. Let's map this out for everyone because it provides the architecture for how this kind of constructed truth actually accumulates.
Imagine a massive tree diagram like a family tree. The circles or nodes on this tree represent specific stages of knowledge construction in time. You start at the root node at the bottom. This represents everything you currently know and have explicitly proven.
Okay, the baseline.
As you run algorithms and construct new proofs, you move up the branches to new, higher nodes.
So it maps the journey of discovery.
Exactly. And in Kripke semantics, knowledge accumulates monotonically. That means if a proposition is proven or forced at a certain node, it remains solidly true for every single subsequent node above it on that specific branch. You never unknow a constructed truth. It becomes part of the permanent foundation.
But there's a catch, right?
Yes. Here is the strict intuitionistic catch. To claim that a mathematical object exists at your current node, you are entirely bound by what is called the existence property, or EP.
The existence property. This is the heart of the Pixar didn't happen rule.
To say something exists, you cannot just point to a contradiction in a neighboring branch. You must explicitly construct a specific, identifiable local variable and use output of verifiable proof at that exact Kripke node. Within this algorithmic ecosystem, existence is inextricably tethered to programmatic demonstrability.
Truth isn't floating around.
No, the truth isn't out there in the void waiting for you. It only exists where you have built the Kripke node to hold it.
So, synthesizing this, intuitionistic logic demands an explicit constructed proof. It refuses to deal in absolute unearned binaries. It wants the algorithm. But here is the massive problem we run into. We are trying to build AI systems and hardware that operate in the physical world.
And the real world is messy.
Exactly. The real world, unlike the pristine realm of the twin primes conjecture, isn't always sharp and mathematically defined. How does an engineered system, which is based on constructed logic, handle the murky, undefinable gray areas of human language, weather, or biology?
Which brings us to a crucial pivot in system design. Pure logic, even intuitionistic logic, requires precise thresholds. But reality doesn't operate on strict thresholds. So we have to introduce a concept called fuzzy logic.
Because there are concepts that inherently lack sharp boundaries.
Consider concepts like temperature or height or safety. Let's look at a classical Boolean logic system programming a smart thermostat. An engineer sets a hard binary threshold. If the temperature hits 30 degrees Celsius, it is defined as hot and the AC turns on.
Okay, simple enough.
Under that logic, 30.1 degrees is 100% hot, but 29.9 degrees is 0% hot. It is mathematically categorized as not hot.
Which is completely absurd if you are a human being standing in the room. You wouldn't step outside into a 29.9 degree afternoon, wipe the sweat from your forehead and say, perfectly not hot today. The real world is a spectrum.
And fuzzy logic was designed specifically to map that spectrum. Instead of forcing variables into a 1 or a 0, fuzzy logic allows for degrees of membership. In a fuzzy system, 30 degrees doesn't have to be a binary switch.
It can be both.
It can have a membership value of 0.8 in the category of hot and a simultaneous membership value of 0.2 in the category of warm. It handles truth as a continuous curve rather than a jagged cliff.
And as we move into the era of advanced AI, this continuous handling of truth isn't just a neat trick, it's absolutely vital.
Think about natural language processing, how an AI understands a tweet or a view. Human language is rarely strictly positive or strictly negative. It is sarcastic, it is nuanced, it relies on context, it is profoundly fuzzy.
For like predictive maintenance for machines.
Exactly. A massive turbine in a power plant doesn't instantly snap from perfectly fine to catastrophically broken in 1 millisecond. It degrades gracefully. It moves through subtle, fuzzy states of wear and vibration. An AI needs to understand when a machine is slightly anomalous versus imminently dangerous.
So we use fuzzy systems to process these gray area realities using if-then rules. Like, if vibration is somewhat high, then reduce speed slightly. But how do we actually write those rules? If the real world is so complex, a human engineer can't possibly sit down and write out millions of fuzzy if-then statements.
They can't. And this is where our old friend, the evolutionary algorithm, comes back into the picture.
Through a powerful hybridization, right? We merge the biological search power of evolution with the continuous logic of fuzzy sets to create genetic fuzzy systems, or GFS.
You've got it.
Let me make sure I understand the dynamic here. If I am an expert at parking a car, maybe I can write down 3 or 4 fuzzy rules for an AI. If speed is high and distance to the bumper is very short, then apply hard brake. But if we are analyzing, say, global weather patterns or complex biological data, human experts don't even know what the rules are.
So you let the algorithm figure it out. You use a genetic algorithm to automatically generate and tune 2 things simultaneously. First, it evolves the discrete rule base, the actual if-then statements. And second, it evolves the membership functions.
The membership function.
Yes, the precise mathematical curves that define exactly what high or very short actually mean based on the raw numerical data.
The sources provided a stunning real-world application of this in the medical field, specifically using genetic fuzzy systems for microarray data classification to diagnose diseases like cancer. We were talking about looking at the expression levels of thousands of different genes simultaneously to figure out if a patient is sick.
This is an incredibly high-dimensional, chaotic space. A human doctor cannot simply look at a spreadsheet of 10,000 gene expression levels and spot the pattern.
It's just too much data.
Way too much. So researchers applied a highly specialized evolutionary approach called the ANT-B algorithm, or ABA, operating alongside a genetic swarm algorithm.
Okay, the ANT-B algorithm. I need you to explain this mechanism deeply, because when I first read the name, I just pictured an insect fight club inside a motherboard. How does this actually work?
It is a beautiful manifestation of swarm intelligence, which is a sub-branch of evolutionary computation. It mimics how colonies of social insects solve complex spatial problems. The algorithm essentially splits the massive medical diagnosis problem in half, assigning one task to the virtual ants and another to the virtual bees.
Let's start with the ants. What is their job?
The ants use ant colony optimization to evolve the discrete if-then rule set. Imagine a sprawling virtual map where every location is a specific genetic marker. The virtual ants start walking randomly across this map.
Okay,
When an ant stumbles upon a pathway of genes that successfully correlates with the correct cancer diagnosis, it leaves a virtual pheromone trail on that path. Over thousands of iterations, the paths that lead to accurate diagnoses accumulate more and more pheromone, attracting more ants. Eventually, the shortest, strongest, most accurate paths emerge from the chaos. Those paths become the concrete if-then rules.
Okay, I can visualize that. The ants are carving the logical highways through the data. So what are the bees doing?
While the ants are locked onto the paths, building the rules, an artificial bee colony optimization algorithm is simultaneously hovering over the data, fine-tuning the continuous fuzzy membership function.
So hovering and tuning us.
Yes. The bees are adjusting the precise dials of those gray areas. They are testing millions of minute adjustments to decide exactly what threshold of gene expression counts as high, medium, or low to maximize the accuracy of the rules the ants just built.
The ants build the structure, the bees calibrate the sensors, and the statistical results of the swarm logic.
Extremely impressive. The ANT-B algorithm generated a fuzzy expert system capable of diagnosing the microarray data with an average of 98.5% overall classification accuracy.
Which is phenomenal for complex disease diagnosis. But the research points out that the raw accuracy percentage isn't even the most important breakthrough here. The true so what insight is the structure of the solution the swarm produced. The algorithm averaged only 5.4 genes per rule and about 2.3 linguistic terms per gene.
Which means the final output is incredibly compact.
Why does that matter to the doctor sitting in the clinic with the patient?
It matters because of explainable AI, or XAI. This is arguably the biggest crisis in artificial intelligence right now. If a hospital uses a massive deep learning neural network to diagnose that patient, the AI might be 99% accurate, but it operates as an opaque black box.
We don't know how it works.
It makes its decision based on millions of hidden mathematical weights and biases. If the doctor asks the neural network, "Why did you diagnose this patient with cancer?" the AI cannot answer It essentially says, because the geometry of my matrix multiplication says so, a human cannot audit it, they cannot truly trust it.
Tying this back to our philosophical discussion, the neural network provides no cryptinode. It gives you an answer, but it refuses to construct the proof.
That is the perfect connection. But a genetic fuzzy system, optimized by our ants and bees, provides a highly compact, human-readable rule base. A doctor can literally read the final output on a screen.
Oh, that changes everything.
It does. It says, if gene A expression is high and gene B is moderately low, then the diagnosis is positive. The evolutionary algorithm has constructed a localized logical proof that the human mind can verify, audit, and understand. It bridges the massive gap between alien machine intelligence and human intuition.
We have covered so much ground today. We started with classical logic crashing into the wall of complexity. We watched EAs throw genetic spaghetti to find false peaks. We saw hardware mutate and heal itself. We questioned the very reality of truth with intuitionism. And we just watched virtual insect swarms build explainable medical logic. But there is a final frontier.
The ultimate synthesis.
The last destination on our deep dive. And it is what happens when this entire process swallows its own tail. We are talking about the Ouroboros of computer science systems evolving their own foundational reasoning.
We are looking at meta-evolution and large circuit models. This is the stage where the boundary between soft stochastic biological search and hard symbolic mathematical logic entirely dissolves. Up until now, we've been talking about using evolution to find solutions to problems. Meta-evolution is about evolving the solvers themselves.
Let's talk about the Sat-Lucian architecture from the sources. This absolutely blew my mind.
At the beginning of this discussion, we talked about classical SAT solvers algorithms like DPLL and CDCL. Those are incredibly complex pieces of software that were meticulously designed, line by line, by brilliant human computer scientists over decades. Sat-Lucian is a framework that turns that entire software engineering process over to the machines.
To the AI.
It uses large language model agents, the same underlying architecture that powers advanced AI chatbots, to autonomously evolve full C++ solver repositories.
This is a massive leap. We aren't just flipping bits in a string of integers anymore. We're talking about an AI writing, compiling, debugging, and testing raw software code aimed at solving logic problems.
The system operates autonomously. The LLM agent proposes a brand new heuristic, a new algorithmic rule of thumb for navigating a SAT problem. It writes the C++ code, compiles it, and unleashes it against a massive benchmark of competition-level logic puzzles.
And it checks its own work.
It measures how fast and accurate its new code is, takes that feedback, and uses evolutionary principles to mutate the code into an even better heuristic in the next generation.
It is an algorithm discovering new ways to think.
And in some instances, documented in the research, these machine-evolved solvers are discovering algorithmic kernels and shortcuts that human engineers never conceptualized. They are outperforming the human-designed champion solvers.
But I have to imagine as these AI-generated circuits and logic systems get larger and more complex, don't they eventually hit a new scalability wall? We talked about the deterministic wall earlier. Surely evolution has its limits when the network gets too monstrously huge.
Yes, evolution struggles with massive scale. When evolving huge logic circuits, researchers encounter a phenomenon known as the curse of skip connections. The evolutionary search gets completely lost in the chaotic, tangled wiring of a massive network. The mutations become too disruptive, leading to imbalanced learning where the circuit just collapses into noise.
So how do the researchers overcome the curse?
One of the most cutting-edge frameworks detailed in the sources is called TNET. It tackles the scalability wall through a synthesis of rigid geometry, classical theorems, and machine learning.
Let's break down TNET. How does it tame the chaos of a massive circuit?
First, instead of allowing a messy, free-for-all grid of connections like early Cartesian genetic programming, TNET restricts the evolutionary search to regularized, triangle-shaped circuit networks. It enforces a very specific, scalable, hierarchical geometry that keeps the wiring from becoming a rat's nest.
Okay, so it provides a scaffolding.
Second, to handle massive logic tables that are too big to process at once, it utilizes the Shannon decomposition theorem.
Which means what exactly?
Imagine you have a massive, incredibly complex wedding cake to serve to 1,000 guests. You can't just try to mash the whole cake into boxes at once. Shannon decomposition is a mathematical method for cleanly slicing a monstrously complex Boolean truth table into smaller, perfectly identical, mathematically manageable subfunctions. It breaks the massive problem down into bite-sized pieces that the algorithm can actually chew on.
So you have geometric scaffolding and you are slicing the problem up. Where does the evolution come in?
TNET uses an evolutionary algorithm to explore the landscape of these subfunctions, but it doesn't do it alone. It is assisted by a reinforcement learning agent.
Wait, it combines evolutionary genetic algorithms with reinforcement learning.
It is a hybrid powerhouse. The evolutionary algorithm maintains a large, diverse population of circuits. Its job is to explore far and wide, ensuring the system never gets trapped on a false peak. Meanwhile, the reinforcement learning agent, which learns by assigning rewards to specific actions, acts as a hyper-focused tutor.
Oh, wow.
It takes the elite, fittest circuits from the evolving population and aggressively fine-tunes their internal wiring to squeeze out maximum performance.
So evolution provides the broad strokes, and reinforcement learning paints the microscopic details. And the result of this hybrid approach.
TNET is capable of synthesizing massive, highly optimized logic circuits containing over 1,200 nodes that significantly outperform previous state-of-the-art human and machine designs.
1,200 nodes. Trying to manually optimize the routing of a 1,200-node dynamic circuit is a level of complexity that the human mind simply cannot hold all at once. But the Ouroboros doesn't stop at hardware design. It loops all the way back to the deep philosophy we discussed with Brouwer, to intuitionism itself.
Yes, the synthesis of epistemic logic.
The sources discuss systems, specifically prologue-based theorem provers, that are automatically discovering epistemic operators for intuitionistic epistemic logic. IL. What is actually happening in that computer?
This might be the most profound application of everything we've discussed. Researchers have built evolutionary search systems equipped with candidate definition generators. These algorithms aren't solving math problems. They're exploring the landscape of logic itself. They are automatically exploring the nuances of modal semantics.
Can you ground that for me? What are they searching for?
They are testing different definitions of necessity and possibility. The algorithm is running automated abductive reasoning.
Abductive reasoning. That's essentially working backward from an observation to find the simplest, most likely explanation, right? Like Sherlock Holmes walking into a room, seeing a broken window and wet footprints, and concluding it must be raining outside.
That is a great analogy. The algorithm is looking at a set of desired logical outcomes and working backward to find the absolute minimal assumptions and rules required to make a formula, a provable mathematical theorem. It is automatically synthesizing entirely new logic systems tailored to specific philosophical interpretations, like the Brouwer-Hating-Kolmogorov semantics we touched on earlier.
So the machine isn't just following the rules of intuitionistic truth, it is actively constructing the rulebook itself.
It is. The machine is discovering the Kripke nodes of philosophy.
If we pull back and look at the absolute grand sweep of this deep dive, what is the final overarching takeaway from all these disparate fields?
The takeaway is that we have entered an era of an integrated continuum. For decades, computer science maintained a strict divide. We thought that biological stochastic algorithms, the fuzzy evolutionary stuff, was only good for soft problems, like image recognition or approximating variables. And we believed that hard symbolic logic, the bedrock of processors and mathematical proofs, required rigid, deterministic, human-designed rules.
But that wall has crumbled.
Entirely. By combining the global, chaotic, exploratory power of biological evolution with the local, verifiable, strict refinement of formal logic, we've created systems that are both functionally transcendent and logically verifiable. The paraconsistent lens proves that the messiness of biology wasn't the enemy of mathematics. It was the key to unlocking its next level of perfection.
I want to try and summarize this incredible journey for everyone listening. We started today with the sheer frustration of rigid classical logic hitting a scalability wall. The million-digit padlock that even supercomputers couldn't crack. To survive, we embraced the biological chaos of evolutionary algorithms, throwing genetic spaghetti at the wall and using psychological warfare like Sewea to manipulate the environment and force solutions. We watched physical hardware literally heal its own battle wounds using the invisible, neutral drift of Cartesian genetic programming. We stripped down our fundamental assumptions about reality with Brouwer's intuitionism, demanding that truth isn't just out there, but must be painstakingly constructed and proven, step by step. We navigated the murky, real-world spectrums of temperature and disease, using the swarm intelligence of ants and bees to create explainable AI that doctors can actually trust. And finally, we landed on the frontier systems like Satlution and TNet machines that write their own C++ code, break down massive logic tables, and even construct their own philosophical frameworks.
It is nothing short of a complete redesign of how computation relates to the concept of truth.
And that leaves us with a final provocative thought, something for you to ponder long after you take your headphones off. Throughout this deep dive, we have established that truth is no longer viewed as an absolute objective reality floating out in the universe waiting to be found. It is something that must be algorithmically constructed, step by step, Kripke node by Kripke node. But if we are now handing over that precise construction process to self-evolving, mutating, swarm-driven stochastic algorithms, what does that mean for the future of human knowledge? Are we approaching an era where our machines construct logical truths that are completely mathematically valid, perfectly optimal, and flawlessly executed, but their underlying reasoning is philosophically alien to the human mind?
We are staring at a future where the proof is undeniable. The skyscraper stands perfectly tall, but the blueprint used to build it is entirely non-human.
We started this hour by comparing classical logic to an engineering blueprint, clean, binary, comforting. But we have stepped completely off the grid and into the jungle. The fixed blueprint is gone. The circuit is alive. And the future of logic isn't something we're going to be able to calculate on a napkin. It's something we are going to have to grow.